Okay, AP Calculus AB, Unit 4, Day 3 office hours. I call this worksheet, I don't know, 4.3a or something. I should check your answers already, but here they are again. Real quick, pause the video if you need to. This was probably on the back side of the notes page. So we got some graphical ones like we've been doing. This is a lot of review. There was some new things in here, in behavior with infinity and things like that. So, move it up. These are just the answers. Of course, you guys should work. Pause the video if you need to. Okay, so let's go through these problems. Okay, these graphical ones, you're saying, well, what's the value of the function at 5? Just assuming these all kind of line up with nice values. That's 3. What's the limit as we approach 5? Well, that's two-sided. Both sides agree that it looks like it's going to 2. What's the limit as we approach 8? Both sides agree that it's going to 0. What's the limit as we approach 1? Well, both sides agree. Looks like 0. E, what's the limit as we approach 2 from the right side? Well, that's negative infinity. What's as we're approaching 2 from the left side? That negative is kind of hard to see, but this is the derivative. Yeah. So from the left side is this side, and the slope is negative infinity. What's the derivative approaching from the right side? Now, some people would say negative infinity also, but it's actually positive infinity. That's a positive slope that's going up, left to right. H, values of x where f of x is continuous but not differentiable. So continuous means connected. Differentiable means it's got to have a corner cusp. So x equals 2, it's not continuous. So x equals 5, it's not continuous. X equals 6, it's not continuous. X equals 8 is continuous but not differentiable. So just x equals 8, just that x value. Okay, so looking at these next ones, we usually just plug number in first, see what happens, and that's a continuous function, so the limit just agrees with whatever the value is. The limit of 6 is x approaches 4. Well, it's 6. 6 is always 6. Okay, this one we get 0 over 0, so that's an indeterminate form. So we could factor the whole out. That's a difference of cubes. X minus 2, x squared, 2 squared, 2x, same, opposite, always positive, over x minus 2. Those cancel. It's a hole in the graph. We plug 2 back in, and we get 4 plus 4 plus 4 is 12. Now, alternatively, we have a new approach where we could take the derivative of the top and bottom and use L'Hopital's rule. 3x squared over 1, plug 2 in, you get 12, which that kind of seemed nice. Sometimes it's not better. I'm going to force you guys to do it both ways on your next test, so you might as well practice it both ways now. Plug 3 in, you get 9 minus 12 is negative 3 plus 3 is 0 over 0. So we could try and factor the whole out. X minus 1, x minus 3 over x minus 3. There's a hole. Plug 3 back in, we get 4. We could do L'Hopital's rule. So that would be the derivative of the top over the derivative of the bottom. Plug 3 back in. 6 minus 4 is... Oh, I made a mistake somewhere. Did I make a mistake here? Oh, yeah, this is 2. 3 minus 1 is 2. 6 minus 4 is 2. I mean, I guess one benefit of doing it two ways is they should both give you the same answer. If you approach 2 from the right side, it's going to be 0 over 0. So we could try and factor the whole out. That's a difference of cubes on the bottom, so it's going to be x minus 2, x squared, 2 squared, 2x, same, opposite, always positive. That's a whole. There's still a 1. We plug 2 in, you get 4 plus 4 plus 4 is 12. 1/12. We could do L'Hopital's rule because we confirmed that it was 0 over 0, which you should show if you're going to use it. And it'd be 1 over 3x squared, which is 1/12. Next one, approaching 3 from the right side, it's going to be 6 over 0. Now remember, in this case, you can't do L'Hopital's rule, but it's 0, but is it positive 0 or negative 0? It's not really 0, it's something tiny. So 3 plus is from the right side of 3, so a little bigger than 3. Minus 3 is a positive difference. So that's going to go to positive infinity. Okay, L'Hopital's rule is not applicable there. This one's going to be 5 over 0. Similar idea, we're approaching 4 from the left, so that'd be like 3.999, which would be a positive number, so positive infinity. Next one, plug 3 in, you get a 27 minus 81 is negative 54 plus 54 is 0 over 0. So we try and factor the whole out. This one, I think we're going to need to use some synthetic division. So it's a 3, so it's 1, 0, negative 27, 54, 1, 3, 3, 9, negative 18, negative 54. Should get a 0 at the end. So it's going to be x minus 3, x squared plus 3x minus 18 all over x minus 3. Okay? So if you plug 3 in, you get 9 plus 9 is 18 plus 8 is 26. I feel like I made a mistake somewhere. Hold on a second. 9 plus, oh, that's an 18, minus 18. So that's 0. Just ends up being 0. L'Hopital's rule would be 3x squared minus 27 over 1. So it'd be 27 minus 27 is 0. So it gives us the same thing. Here we're approaching 6 from the right side. It's going to be 36 over 0. But is it positive 0 or negative 0? So 6.001 from the right side would be a little bigger than 6. This would end up being negative. This would be negative infinity. L'Hopital's rule doesn't make sense on that one. 11, if you plug 0 in here, cosine of 0 is 1, plus 1 is 2 over 2, which is 1. That's it. Nothing weird. Infinity. Now we go infinity, it's going to be positive infinity on top and negative infinity on the bottom. This is a dominant term, this is a dominant term. Now, I'd like you to show this and then just say, okay, well, the dominant terms, they have equal exponents, so it's really just a ratio of their coefficients. 4 over negative 2 is negative 2. That's the easiest way to do it. You could do L'Hopital's rule, which is not easier. In fact, it's quite a bit more work. So you take the derivative of the top and bottom, and you would still get infinity over negative infinity. So you have to do L'Hopital's rule again, which you're allowed to do. And you would get 24x over negative 12x, and you would get positive infinity over negative infinity. So you have to do L'Hopital's rule again. And you'd finally get 24 over negative 12, which is negative 2. So what's easier? Dominant terms or L'Hopital's rule? Dominant terms. Same answer. It works. Okay, 13. Dominant terms. It's going to go to positive infinity over positive infinity. We should get a positive answer. It's an indeterminate form. I'm not going to do L'Hopital's rule on these. You just saw how much extra work it was. Now, this dominates this guy. So the bottom's going to get way bigger than top, and it's going to go to 0. Simple. This is all the work you got to show. Dominant term is going to be negative infinity over positive infinity. So you should get a negative answer. The one on the top is bigger than the biggest one on the bottom. So the top's going to blow up, and it's going to go to negative infinity. It's going to blow up, but it's going to be negative. This one will go to negative infinity, which can make a difference. So the top's going to be negative infinity, and negative cubed, over positive infinity, because the negative cubed is negative with another negative. Those are the dominant terms. They have the same degree. So it's really just going to be the ratio of their coefficients, negative 2/3. Okay, L'Hopital's rule will be a lot more work on those. Now here's some interesting ones. This is the dominant term here. This is the dominant term here. There's a square root around it. It's going to be some kind of negative infinity over some kind of negative infinity, which you can't take square roots of negatives, but they're going to end up becoming a positive, right? So we should get an answer. But those are the dominant terms. And so it's really just going to be, they have the same degree, so it's going to be the ratio of their coefficients. So that's the square root of 4 9s, which is going to be 2/3. Okay, here we're going to positive infinity. There's a dominant term. Here's the dominant. Only one of them is inside the square root, but that's going to get really big. It's going to be some kind of positive infinity. On the bottom is going to be some kind of positive infinity. So, by the way, we could do L'Hopital's rule on these, but I don't think you want to. I think it's quicker without it. Now, you got to be careful because you might be like, oh, well, this is going to be 2x, right? Because essentially we're ignoring these and we're saying, well, square root of 4x squared is 2x. So you might at first think, oh, the top's going to grow way bigger than the bottom. No, they have the same degree, actually. So it's really just going to be the ratio of their coefficients, 1/3. You got to watch out on these, though, because I'm going to show, I think the next problem we'll see. This is going to negative infinity. It gets squared, made positive, times 4. Square root of it's going to be positive infinity. On the bottom, it's a negative infinity. So we should get a negative answer. Now, this is the dominant term on top. This is the dominant term on the bottom. This you're going to end up taking the square root of. And then you'd say, oh, well, let's take the ratio of their coefficients, 2/3. But that's not the right answer. First of all, you should know we're going to get a negative answer right here. That's one of the benefits of writing this down is to be like, oh, a positive or negative is a negative. And you got a positive answer, and it doesn't make sense. The reason is that this x right here, you're kind of thinking, oh, I'm plugging negative in over negative here, so the negatives cancel out. No, the negative got forced to be a positive, and then when you took square root of it, it was still positive. But now, if you just write 2x, it's like it's going to be negative. Now, you got to put absolute values around it. This is something you guys learned how to do in Algebra 2 when you simplified radical equations. That sometimes with variables that came out, you had to put these absolute values around to ensure they had the sign that they should have. So that means the top's going to be positive, but the bottom's going to be negative when you plug in negative infinity. So it's going to be negative 2/3. Okay, now on the last problem, we got lucky, but we should have done that here too. We should have put absolute values around it. So I'm going to expect that in the work. When you take an even root of a variable to an even power that got forced to be positive, and when you take that even root and you have that variable to an odd power now, and that negative is going to act like it's going to come out, and it's not. You got to force it to happen. Here we're going to negative infinity. This is the dominant term. This is the dominant term. This is going to be 4x cubed. Now, if we just plug negative infinity in, it gets raised. It's going to be positive infinity, and here it's going to be a negative cubed is negative times negative is positive infinity. So we should get a positive answer. Here we wouldn't necessarily need to put. Yeah, we would. We would need to put the absolute values around this. You might get lucky this time, and it's just going to be. Well, no, we should get a positive answer when we're done. So if you just did it like this, you would have said, oh, it's 4 over negative 2. So the answer is negative 2. No, the top is going to be positive and the bottom is going to be positive. And if you put these absolute values around it, that should take care of it. So it's going to be positive 2. Okay, so you just got to watch out on those. I guarantee I'm going to give you some of those on your next test or whatever. Here's piecewise. Now, the technical way of doing a piecewise, we've done this on some other problems in past homework assignments where they've kind of let you is to do the left side, because the left side and the right side use different functions, right? So the left side is going to be x squared, which gives you 9. And then the right side limit as x approaches 3 from the right side of f of x is going to be the other function, which is 4x minus 3. So you plug 3 into that, and you get 12 minus 3 is 9. And now, because they agree with each other, the answer will be 9. If they didn't agree, then you'd say does not exist. This one's kind of interesting. You plug h equals 0 in. It's going to be 2 cubed minus 2 cubed is 0 over 0. So this is one that you can use L'Hopital's rule on. But what I want you to recognize, and I think I'm going to be bringing this up soon, is that this is actually a derivative. I don't think I've gotten to this in class yet, so this is a sneak peek. This is the derivative of x to the third power, and the derivative of x to the third power is just 3x squared. And so then we would plug a 2 into that, and we would get 12. The answer is 12. Now, you could blow this all up. You know, it'd be a bit of work to FOIL this out. I mean, it's going to be 8 plus 8h plus 2h squared plus 4h plus 4h squared plus h cubed minus 2 cubed, which is 8, and those cancel out. So then you could factor an h out of everything, and it's a hole in the graph, and you would eventually get 12. But like I said, I'm going to show you some new trick here. Now, sandwich theorem, if you plug infinity in here, you're going to get infinity on the bottom, and then like sine of infinity, which is what? Now, in reality, it's somewhere between -1 and +1, right? Sine never goes above +1 or -1. Divided by a huge number. I mean, I think we could comfortably say, well, any number between -1 and 1 divided by infinity is going to be tiny. It's going to go to 0. Okay, but it's hard to show the work for that. I think logically, maybe we could, understand that in our head. So here's the work. It's called the sandwich theorem. So you start with sine x squared is between -1 and 1. Okay, that's true for sure, right? We could divide by x to the 4th, right? Middle, left, right. That's okay to do. And then we could say, okay, well, let's take, as x goes to infinity, this guy goes to 0, this guy goes to 0, and we've said that this has to be between these values or equal to it. So this guy has to go to 0 now. It's sandwiched between these two. They also call it the squeeze theorem. Okay? And that's a really kind of lazy way of writing it, but it's got to be 0, right? I mean, this, as x goes to infinity, this expression has to be between the limits of those going to infinity, which is 0. So it has to be 0. So this one, this is a similar problem here. You just plug it in. Now, I think I'd be comfortable in saying, oh, well, this is going to be 0 because it's some number between 2 and -2. So we're going to say, okay, well, sine x cubed is between -1 and 1, right? And then we can multiply everything through by 2 over x squared. And then we could say as x goes to infinity, this only works in this case when x goes to infinity. This is going to go to 0. This is going to go to 0. So this is going to have to go to 0. And the answer is going to be 0. So that's the sandwich theorem. We will use that sometimes. Okay, so that's it for this worksheet. And there was one other worksheet that you were asked to do. So this was kind of a quick one. I did all the problems. I did a lot of them multiple ways. So